Alright, welcome back, and good afternoon. So, I graded your homework, posted some comments on that, and I don't want to say surprisingly because I have great confidence in this class, but, you know, somewhat surprisingly from a statistical point of view, mostly everybody nailed the homework perfectly, which is fantastic, and really doesn't happen very often. So, so it seems like this stuff is making sense, which is awesome. So I graded some of the questions in particular, and I looked at some of them but didn't grade them. So 2.1 question 3. This is a product rule question. So you have a shirt, 4 sizes, 6 colors, and a choice of 3 emblems, including no emblem. So 3 choices for what you want on the pocket. And that's just a product rule. So first you choose a size, then you choose a color, then you choose a decoration. And you can do those 4, 6, and 3 ways, so you multiply that. That's the number of choices. Yeah, it is chapter 2 in the text, which doesn't usually mean it's necessarily easier than, you know, chapter 5. Maybe just that it has to come first. But for whatever reason, people seem to get this, which is great. Number 5 we talked about in class the other day, which was the fact that you're taking a picture with 6 people and the arrangement matters. The fact that they're in 2 rows does not matter, though. You perform this task as a set of 6 subtasks. Choose who goes in position 1, position 2, position 3, and so on. So it's just a straight product rule. 6 times 5, 4, 3, 2, 1, 720. And then the meal question. So main course, you have 3 choices. Vegetable, you have 2, and dessert, you have 3. I would want, you know, ice cream on my cake or pie, so I would prefer to have that choice. But 3 desserts, and so again, that's a product rule, right? 3 times 2 times 3, a total of 18 possible meals. Cool. All right, and then question section 2, we start getting more into you know, looking at things in terms of permutations and combinations. So 3 raffle prizes out of 1,000 tickets, and they're different prizes, and the word different here is important. You're not just picking 3 winners, you're choosing 3 particular, you know, a first place, a second place, a third place. So that's the number of 3 permutations of 1,000 objects. So so that looks like P1000, comma 3. Let me make that more legible. And everybody that I looked at their homework did exactly what I want you to do on homework and on a test, which is give me your answer in terms of, you know, some kind of formula. Ideally, you know, something like this, or this times this times this, or this. And then if you want to actually figure out what the number is, you know, write out that big long number. But this is much more important, right? If I see this, I know you understand the setup of the problem. If I see this or this, I know you know how to calculate the number of permutations. And then the actual number is, do you know how to punch the buttons on your calculator, right? And if you make a mistake with that, I don't care, right? I'm not going to take off points for that. As long as I know that you were trying to do the right formula, right? It's not a key punching class, so I don't think I would take off points for that. All right, and then how many 8-letter words can be formed from the 26 letters in the alphabet? And there's arguably 2 ways to interpret this. The first is an 8-letter word could contain the same letter more than once. So, you know, this would be a perfectly valid put this on a separate window. So this would be a perfectly valid word. And usually when we think about, you know, a four-letter word, we don't require that each letter be different. And so the number of ways we can make an 8-letter word out of 26, well, that's just going to be, you know, 26 to the 8th. It's the product rule where each task can be done 26 ways. But in a unit that's talking about permutations, right, we could think of this as perhaps asking, you know, a Scrabble question. You have 26 Scrabble tiles with the letters A through Z, and how many words can you make out of those 26 letters? And so in that case, there's no repetition allowed or possible, and so that's the number of ways that you can choose 8 things out of 26. And there the order does matter, so it's actually the number of 8 combinations of 26 objects. Sorry, so that's permutation. The order does matter. And then the usual formula for factorials with that. And then the basketball question, so 5 starting positions and 15 players that can play any position. So now you're just choosing who are the 5 people that are going to make up this team. And if they can play any position, it doesn't matter which you choose. So that's, you know, another permutation question. 15 times 14, 13, 12, 11. But then if the center has to be one of 2 players, so yeah, you need to know that the center is a position. And so we're told that there are only 2 people who can fill that particular position. So now we have 2 tasks. T1 is choose who's going to play the center position. And then T2 is fill the other 4 positions. So there's 2 people who can play the center. There's 2 ways to make that choice. And now we have another problem. We have 14 players and 4 positions. And so we need to know, you know, which player is going to take position 1, position 2, position 3, position 4. And so that's, you know, product rule or a permutation. And then we end up taking the product of these because this is a product rule. Choose the center for the first task and then fill the other positions. I never realized how common center was in sports. But yeah, you're right. Interesting. Sports are strange, man. There's some sociology I'd love to do on sports. All right. And then I don't think those were jokes. I think they were just observations. Although the center doesn't actually kick the touchdown. Unless it's a trick play. Okay, question 7 we did in class. Principle of inclusion, exclusion lets us know that, you know, 47 plus 42 minus 17, that's the size of the union of tennis players and swimmers, which will turn out to be 72. And then if you subtract that from the size of the universe, you get the size of the complement, which is 18, participated in neither. Yeah, I grew up watching the Redskins, which was always about trick plays. And I love their new name, Washington Football Team. That's like totally cool. Let's see. Number 7 in section 2.3 was poorly worded, or is that just me? Well, I mean, if it's poorly worded to you, then it's poorly worded to you. Survey of 90 people, 47 played tennis, 42 swam. 17 participated in both. So there's other questions like this in the book. For example, 15 people saw Star Wars and 20 people saw Raiders of the Lost Ark, and 10 people saw both. So how many people saw only one movie? Right? Questions like that. So it's about making some sets. So T could be the set of the people who played tennis, and S could be the set of the people who swim. And now you can try to figure out, the size of these things. And if we're told 47 people played tennis, well, then the number of elements in the set T is 47, if this is, the names of each person who played tennis. And if we're told that 42 people swam, then the number of things in S is 42. And we're told the number of people who did both was 17. Well, if you did both tennis and swimming, then you are in the intersection of these sets. You're in both of these sets. And this is 17. And we want to find the number who participated in neither, which means we're looking for the complement of this set. So the number of people who are not in either T or S, or both, right? And so first we want to find the number of people in this union, right? And that's principle of inclusion exclusion. This plus this minus that. And then if we know the cardinality of the universe is 90, then if we take the complement of a set in the universe, we subtract the size of that set. That'll give us the size of the complement. So it's not totally direct or obvious. It takes some interpretation, but it's the setup for a number of problems that we'll encounter. All right, where are we here? And yes, the answer in the back of the book for number 7 is wrong. All right, let's see what else is on here. And then 2.1, I looked at questions 1 and 3. So Judiciary Committee made up of 3 faculty members and 4 students. There's 10 faculty to choose from and 25 students, and most people got this correct. This is a combination problem. So you have 10 faculty, and you're trying to choose 3 faculty members. And then you have 25 students, and you're trying to choose 4. And the task of forming your Judiciary Committee is, comprised of doing this task and then that task, and so the product of the number of ways to do each is the number of ways you can do the entire task. So that's the number of Judiciary Committees that are possible. And then number 3, so this was the other one that I looked at, number of subsets containing at least 7 elements. So we have 10 elements in a set. Let's just think about forming a subset of 7 elements. A subset is going to be made up of elements from the original set, which means each of these 7 elements is going to be chosen from this original set. And the order in which we choose them does not matter. I could choose this element, this element, this element, and then these 4 elements. Or I could choose these 4 elements, and then this, and this, and that. The order in which I choose them doesn't matter. The only thing that matters is what is the actual choice I made. Which 7 elements did I select from this original set of 10? Thank you. So 10 elements. we're forming a subset of 7. So I could pick, these 3 elements and these 4. Or I could pick, this element, this, and then those 2, and this 1, and this 1. Or I could pick, these 4 elements and then these 3. And they all correlate to the same subset, right? The order that I pick them in doesn't matter, so it's not a permutation question, it's a choice question. The only thing that matters in determining the nature of this subset is which 7 elements did I choose out of these 10. And so the number of ways I can do this is just 10 choose 7. So that's the number of 7 element subsets that I can pick. And this whole thing is a sum rule. So yeah, you got it exactly right. It's a sum rule. I can complete the task of making a subset of at least 7 elements by doing any one of the following. Either make a subset of 7 elements, or one of 8, or one of 9, or one of 10. So this is the number of subsets of 7 elements. This is the number with 8. This is the number with 9. This is the number with 10. And it's a sum rule. So this is the total number of possible subsets. And once again, if I were to extend this, this would be the number of all possible subsets. Right? This is the number of subsets of length 0, 1, 2, 9, 10. But we know what the number of possible subsets of a 10-element set is. It's 2 to the 10th. And so this sum must equal 2 to the 10th. And that's that sum of that row of, the 10th row of Pascal's triangle is equal to 2 to the 10th. That's one way to see where that property comes from. I don't feel bad about that. A number of people did that. And that's the biggest part of the answer is knowing that that's the number of 7 element subsets. But then you just have to back up and, do 8, 9, and 10 also. Homework is meant to be like, a learning exercise. So if you can totally rip through your homework, you're probably, not learning a lot, which means either you already knew this stuff or I'm not teaching enough stuff. So having problems on the homework is actually, it's a good sign that you're getting something out of this. All right, expanding 2x minus 3y to the 4th, so that's just a big long binomial expansion. I'm not going to write that out, but it's this thing to the 4th plus this thing cubed times that multiplied by 4 choose 1, which is 4, and then that thing squared times that thing squared multiplied by 4 choose 2, and so on. And just remember, this term is negative 3y, so when you raise it to an odd power you get a negative. So that's just keeping track of that. Let's talk about number 13. So 13 is a fun problem. 10 points, and none of them are collinear. Okay, so that's important. So boom, 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 boom. There's 10 points. Presumably none of them are collinear. How many lines can we draw through these points? So what is it that determines a line? That's a poorly worded question, but yeah, I knew someone would get it. 2 points, right? Or 2 vertices. If we have 2 points, that defines a line. All right, so this is unnecessary, but it's so rare I get to use a straight edge in this class. So, here's 2 points. There's a line going through them. Here's another 2 points. There's a line going through them. Any 2 points determine a line. Right? There's 2 points that, one of the points already got used. That determines a line. And as long as no 3 points are collinear, right, any 2 points will give me a different line from any other 2 points. Now, if I have another point right here, right, these 2 points and those 2 points and those 2 points would all give me the same. But as long as that's not the case, right, any 2 points give me a line. So how many lines are there? Well, how many pairs of points are there? I don't know. But we have 10 points, and we want to choose 2 of them. How many ways can we do that? It's just 10 choose 2. And whether I choose this point and that point, or I choose that point and this point, I get the same line. So the order in which I pick these doesn't matter. So this is just 10 choose 2. And if I was looking at vectors, where I would pick 2 points and one would be the starting point and the other would be the ending point so that these had directions, then the order would matter. Choosing this point and this would give me a vector going like that, whereas choosing this point and that would give me a vector going like this. That would be a permutation question. And guess what? P of 10, 2 is 10 factorial over 8 factorial. C of 10, 2 is 10 factorial over 8 factorial times 2. So the number of permutations is exactly twice the number of combinations. Well, that's because if we allowed arrows on these lines, we have twice as many directed lines as we do just plain undirected lines. So this works, right? It makes sense. And then for the last part, for triangles, so exactly the same thing. How many points determine a triangle? 3. And anytime you pick 3 points, you get a triangle. So here's a triangle, and here's a triangle, and here's a triangle, and here's a triangle. And the total number of triangles that I can draw by connecting these points is the number of ways I can pick 3 points out of the 10. And that's just 10 choose 3. So that's a nice geometric interpretation of these combinations. Easy peasy. Awesome. All right, any other questions on the homework? All right, well, let's continue. Let's see, I feel like I worked with trees in some elementary or middle school math class in the past or something. Really, with trees? Could be. I know I worked with modular arithmetic in 6th grade because that was when like new math was coming out and they were trying to teach kids modular arithmetic. It probably warped me. And sometimes we diagram sentences in school, and that's very similar to what we're going to do next week in here, which is automata theory and phrase structure grammars and things like that. So yeah, we bump into this stuff. All right, so let's look at graphs, and let's look at paths through graphs. So let me give you a bit of a definition, because I haven't given you any definitions in a couple of days. So a graph G, which is made of vertices and edges, is connected if there exists a path between U between u and v for all uv in the set of vertices. Well, what do we mean by a path here? So loosely speaking, it's a way to start from one vertex, and by following edges from one vertex to another, to another, to another, eventually end up at this second vertex v. So kind of the intuitive notion of a path. So here's A, B, C, D, E, F, G. So is there a path from F to G? Yeah, there's a few of them. We can go from F to B to C to G. We can go from F to D to E to C to G. We could go from F to D to E to A to B to C to E to A to B to C to G. There's lots of paths we can take. But as long as there's at least one path between every pair of vertices, then we say this is a connected graph. So what does it mean when it's not connected? Something like this. And there's no path between F and H, for example. Alright, again, we'll mostly stick with connected graphs. And if this is an undirected graph, if our edges don't have arrows on them, then, you know, all we have to do is find some collection of edges from the starting vertex that eventually gets us to the ending vertex. But if it's a directed graph, we have to follow the arrows. So from A, we can go to B, and then C, and then to G. But we can't go from A to E to C, right, because we can't go against that arrow. But we could go from A to E to D to F to B, and then from there go to C and go to G. And from G, we can't get anywhere. The way I've drawn this graph, right, we have one edge going into G, but nothing coming out of G. And so G doesn't let us get, there's no path starting from G leading to any other node. And so we'll talk about circuits. And a circuit is a path that starts and ends at the same vertex. So you know, if I start at L and I go to J, I, H, K, and back to L, that's a circuit. Or if I go from K to Q to N to I to H and back to K, that's a circuit. So it's a closed path. Alright, the length of a path is the number of edges that you travel along in following the path. And this will include multiplicities. So if I were to go from Q to L to J, this path has a length of 2. If I go from Q to L to J to I, that path has a length of 3. If I go from Q to M to I, that path has a length of 2. So we can start to ask about shortest paths, right? What's the shortest number of edges I need to get from one vertex to another? Is the first one a circuit? Yeah, so Q, L, J, I, M, Q would be an example of a circuit. So circuits are a type of path. So like A, E, C, B, A would be a circuit. But there's no circuit, and even if we ignore the directions, if we just took this as an undirected graph, there's no circuit that includes G, right? Because if I start following a path from anywhere and I get to G, if it's directed, there's no way to get out of there. But you know, that would be a path, and this would be a path, and so on. Another path from Q to J would be this. Go like this, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There's a path of length 22 from Q to J. So sometimes we'll look at, you know, what is the smallest number of edges from here to here, but when we talk about a particular path and you want to know its length, it's just the number of edges that you traveled along, or one less than the number of vertices that you visited. And I could have a path of, you know, some huge length from Q to Q by just, you know, looping around a circuit a bunch of times and ending up back at Q. All right, and we're talking about this because there are particular types of graphs that have particular types of paths in them. So an Euler path is a simple path that contains every edge. All right, so what is a simple path? Don't travel over the same edge more than once. So let's make a graph. All right, there's a graph. Technically, this is a path. I could start here, and I could go out here, and come back, and go out, and come back, and go out. Okay, technically that's a path from here to here. It's not a simple path. Okay, a simple path, we're only going to visit an edge once. So if I come out from here to here, I'm not going to go back across that path again. Alright, so what's an Euler path? It's a simple path that contains every edge. So basically, it's a bendy straw that you can make into a particular shape. So for example, can we find an Euler path through this graph? Can we find a simple path that contains every edge? And it turns out we can. For example, I can start here and I can go like this and come down here and go up there and then come along this. That's an Euler path. And we need to have this notion of a simple path, otherwise this is trivial. We could always find a non-simple path because, you know, we can backtrack basically. So we want to find a path that travels along every edge without backtracking. All right, and then there's a notion of an Euler circuit, which is a circuit that contains every edge. So I can't find an Euler circuit for this graph, right? I can't find some kind of path that lets me start at some point, travel along each edge exactly once, and come back to my starting point. All right, so is there an Euler path through this graph? All right, where do I start from, and what order do I visit the vertices in? So A to D, and then where? I'm at D, so I got to go from D to B. B to A to E to D, I think you got it, D to C, and C to B. Perfect, that's an Euler path. Very nice. So we can ask, you know, given an arbitrary graph, is it possible to find an Euler path? And is it possible to find an Euler circuit? So here's a graph we can do both. We could start here and we could come over and down and go like that. And we visited each edge exactly once and we ended up where we started. So that has a path and a circuit, an Euler path and an Euler circuit. This is not going to have either. No, this has a path, but it doesn't have a circuit. That's the one we just did. Let me show you a worse one. So this is a path, no circuit. Alright, this one has no Euler path and no Euler circuit. There's nowhere we can start from that will let us travel along every edge exactly once. We're going to have to retrace our steps somewhere. So is there a quick way to tell? So there's this famous question, the 7 bridges of place I can't pronounce because I'm American, but it was a an area of town where there were you know, these 7 bridges, and people wondered, is it possible to walk across every bridge without having to travel across a bridge more than once? And I don't think you can have a circuit without a path, because a circuit is a path. It's just a path with some extra characteristics. So if you have a circuit, you definitely have a path. So this was the graph problem that Euler was presumably considering. That's easy for you to say. And it's a graph problem, right? If we think of these as edges and the points connecting, you know, an end of one bridge to an end of another bridge as vertices, then it's a question of, you know, traveling through that graph along an Euler path. What we now call an Euler path. He didn't call him that. And I think it turns out to be impossible in that case. So is there a way to tell this? There actually is. And it has to do with the degree of the vertices. So here's the theorem. This has got to be a connected graph. It's got to be undirected. It can't have multiple edges going from one node to another, etc. So, you know, a standard graph of the type that we've been talking about this week. There is an Euler path if and only if there are exactly two vertices with odd degree or all vertices have even degree. Is it possible to have only one vertex with an odd degree? Not a bad guess. Remember, if we add up the degree of all vertices, we should get twice the number of edges, which means the sum of all the degrees has got to be an even number. So if there's only one vertex with odd degree, we'd be adding a bunch of even numbers with one odd number. We're going to end up with a sum that's odd. So we can't have exactly one vertex with an odd degree. You could have two, in which case there is an Euler path. You could have none, in which case you have an Euler circuit. Or you could have more than two, in which case you have neither an Euler path or an Euler circuit. Königsberg. Okay, cool. All right, now I know how to pronounce it. All right, and it turns out that if you have the situation where you have two vertices of an odd degree, all you really need to do is start at one of those vertices with an odd degree and finish at the other one. And it's pretty easy to find your Euler path. So here's the one I was taught in school. This was more of the new math stuff, right? So look at the degree of the vertices. So this has degree 2. These have degree 4. And there's no point in the middle. That's just where edges cross. But these have degree 3. So we have to start at one of these corners and end at one of those corners. And we could do that. Maybe we could start here, and you can just kind of go like that. And if you put a vertex in the middle, that's got degree 4 also. We can still find an Euler path through that. So as long as you start at one of the odd degrees, you can just kind of, you know, follow whatever you can. Like that. There you go. So that's a nice, well-defined condition for existence of an Euler path or an Euler circuit. May not necessarily tell us what that path is, but we know it exists. And why is this the case, right? How did Euler figure this out? Well, you can do an induction argument. basically imagine that you have a situation where you have an Euler path through some kind of graph, and now you want to add more edges, right? If I draw an edge from one of these points, right, I'll have two possibilities. I can be coming out of a place with an odd degree, an even degree, right, which will make this degree odd. And unless this reconnects with either the starting or the ending point, I'm going to have an edge I can't travel across. So this has got to join up with one of these odd degrees, which will make it even, which will leave me with exactly two odd degrees. You got to do some work around that, but that's the general idea for an inductive argument. And more hand wavy, right, as we're following a path from vertex to vertex, right? If we're starting at some point, well, you know, we start off when we leave that, we're using up one edge of the degree, right? And if we finish at a point, we're going to come into this vertex, so we're going to use one edge of whatever its degree is. But all the other points in the middle, all the other vertices, what are we going to do? We're going to arrive at that vertex and then we're going to leave. And we're going to therefore travel along two of the edges that make up whatever the degree of that vertex is. And if it's not the place we started or ended, every time that we come to this vertex, we're going to have to leave, which is going to use up another two edges of its degree. And if we add up the total number of edges that we traveled along through here, and in each visit, you know, we had two edges involved, one that we came in, one that we left on, then the total number of edges going through this vertex is going to be even. And that's going to be the case everywhere except where we start and where we end. And where we start and end, we could have that situation, or it could be that, you know, we began here, and when we leave, that'll have a, you know, one edge contributing to its degree, and we might come back at some point. But if we're not ending at that point, then we're going to have to leave again. That will add two more to its degree. And so this will be 1 plus, you know, 2 times some number. And the same thing where we end. Every time we come through here, we have to leave. So that will be an even number of edges contributing to this node's degree. But if we end here, there'll be one time that we arrive, but we don't leave. So it'll be 2 times something plus 1. So that'll be odd. Cool. And in the case where you start and end at the same point, then you've got everything being even degree, and that's the case where you have a circuit because you started and ended at the same point. So yeah, these people were really clever. I'm digging the colors on my little house there. Alright, so those are Euler paths. The other thing we can talk about is Hamilton paths. So Euler paths, we're trying to visit, we're trying to travel along each edge exactly once. With Hamiltons, we're trying to visit each vertex exactly once. So a Hamilton path visits each vertex once. So what's a Hamilton path through here? That's easy, all right? We don't have to visit every edge. We just have to visit each vertex exactly once. And so this is a Hamilton path. It's also a Hamilton circuit because we can do this path by starting and ending at the same point. So this is a path in a circuit. For this graph, we can find a Hamilton path. We could start here and simply go like that. So there's a Hamilton path, but there's no Hamilton circuit. There's no way that we can find a path that begins and ends at the same vertex and visits every vertex. I don't know what a Hamilton Euler circuit is. I've never thought about that. If you can visit a vertex once, I've got a feeling we could make an argument about that pretty simply. Just by doing a counting argument on number of vertices and number of edges. I gotta think about that. Or you should think about that. Wouldn't starting at a vertex still count as the path visiting it? So, yeah, so this is a Hamilton path, but a Hamilton circuit needs to end where it starts. So to find a Hamilton circuit, we need to visit each vertex, but end up at the vertex we started at. And the basic issue is if we start here, there's no way we can get back here, right? It's not a simple path if we go like this, and then we come back, right? And we end up visiting this vertex twice. And if we start somewhere else, like right here, right, once we come out here, we can't get back to pick up that node and get back to our starting point. But this is a Hamilton circuit, right? We can start at this vertex, we can visit this one, then this, and this, and this, and then come back to where we started. And it's a simple path. We haven't traveled along an edge more than once, and we visited every vertex, and we ended up with the vertex that we were that we started from. So yeah, that is a Hamilton circuit. And yeah, the vertex that you're starting at, you are visiting, right? So you get credit for visiting this because you started from here. It's just that for it to be a circuit, you need to end up there also. But it does work as a path. And in this one, there's no Hamilton path. And no Hamilton circuit. A circuit's a path, so there couldn't be a circuit if there wasn't a path. So no Hamilton path through here. Again, if you start here, you can pick up that vertex. But there's no way I can get to here except from here. And if I get to here, I've missed either this node or this node. And if I go to that, then I have no way to get back here. And same thing if I start here, and if I started one of these, I'm definitely going to be missing one of these. Because once I visit this vertex, I have no way to get back to the main cluster. No, I guess we don't count visiting the vertex at the end as visiting it again. I would count starting there as visiting it, but I would say when we're trying to find a Hamilton circuit, we're ending up at the same vertex we started at. So maybe you could technically say we're visiting that vertex twice. But yeah, you're right. Technically, we are visiting it again. The thing about Hamilton paths and Hamilton circuits is there's no general nice clean formula like there are for Euler paths and Euler circuits. It's a much harder problem knowing whether or not one of these paths or circuits exists. Yeah, I think that's a semantics thing. which we will deal with next week, because we will talk about phrase structure grammars. So general criteria for this, very difficult. So let me show you an application of Hamilton circuits. You may like this, you may hate it, but I'll show you anyway. So I'm going to draw a very funny looking graph. Remember, the way that you draw a graph doesn't really matter. It's just the connectivity that makes a difference. So I'm going to draw a graph that looks like this. All right, that's a fine graph. And I'm going to label my vertices in a funny way. Yeah, could be 3D. Man, I got lost looking at YouTube videos yesterday of people drawing these crazy three-dimensional things on paper. Just insane stuff, what people can do. All right, so I've got a graph with 8 vertices and 12 edges, and I've labeled my vertices totally randomly as 3-bit binary numbers. And the question is about Hamilton circuits. And we can say, is there a Hamilton circuit through this graph? And there is. And so if I start from this vertex labeled 0, 0, 0, what can I do to visit each vertex exactly once? Alright, so there's a path through my graph. Now what's cool about this graph is if I think of the vertices as actually being 3-bit binary numbers, they also correspond to coordinates. Right? I could think of this as some kind of XYZ plane. And that's right-handed. And I could think of these numbers as being, you know, how far am I in the X direction, the Y direction, or the Z direction. And that's not the only path. We could find other paths. Right, I could go up like this, and then come across, and go up like this, and come back. The thing to notice about the way that I've drawn this out is that when I follow an edge from one vertex to another, I'm basically moving in one of these coordinate directions, which means I'm changing either my x coordinate from 0 to 1 or 1 to 0, my y coordinate from 0 to 1 or 1 to 0, or my z coordinate 0 to 1, 1 to 0. But any of these edges that I travel along, I change one coordinate value, which means I change one bit of my vertex name. And so if I write down the names of my vertices along this Hamilton path, what do I get? 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 111, 101, 100, and then back to 000. Anybody recognize this pattern? It's another 250 pop quiz. It looks like counting in binary, but not the way we normally count. Right? 0 through 7, we normally do this. It is mirrored. It is like a K-map. Looking for a magic word, starts with a G. It rhymes with Ray. Gray code, perfect. First try. This is 3-bit gray code. I don't actually know if it's an E or an A. I've never figured that out. I should hang around Gothard more. This is reflective gray code. So remember, this is how we normally count in binary. This is weighted positional notation. And when we do state machines, this is a problematic way to move from one state to another. Because when we move from state 3 to state 4, all 3 bits are changing. And if they change at exactly the same time, we'll be in state 3, we're in state 3, we're in state 3, blink of an eye, suddenly we're in state 4. But if things change at different points in time, if the path lengths between this flip-flop and that flip-flop are different, what can happen? We can be in state 3, and then maybe this flip-flop turns on and we temporarily go into state 7. And then maybe this flip-flop turns off and we go into state 6. And then this flip-flop finally turns off and we go into state 4. And it's possible that state 7 is the emergency shutdown state, which says, you know, the reactor is overheating, shut down the power grid. And, you know, maybe state 3 is like, you know, time to turn the lights on, and state 4 is time to turn the lights off, right? And in going from this value to that value, we temporarily go into this very desperately important state 7 that's not really part of our transition, but might be long enough of a transient to trigger some kind of catastrophic event. I think you're right. I think it is gray code, right? So this is why satellites crash. This is why rockets explode on the launch pad. This is why, you know, really bad things happen sometimes, is because of these tiny little transients that turn on for a few nanoseconds. But, you know, in the brain of a computer, a few nanoseconds is, having someone yell at you for an hour, turn off the light, turn off the light, turn off the light. So a gray code can avoid this situation because as we count from one position to another, only a single bit changes. And it doesn't matter how long it takes to change from this number to this number. The only thing that's going to happen is this bit's going to change from a 0 to a 1. And if that happens quickly or that happens slowly, we're just going to sit in state 3 for a longer time and then suddenly go into this new state. So a lot of times when we make state machines, we order our states according to this gray code, and it can come out of simply looking at a Hamilton circuit through a graph where we've, laid out the vertices as binary numbers according to their coordinates. And it works as a gray code because when you move along any edge, you're only changing one coordinate, which means you're changing one bit. And the mirror part, somebody mentioned this was kind of mirrored. So this is called a reflective gray code. So quick rehash of 250, or if you haven't had me for 250, I don't know if you've seen this or not. How do we count in regular weighted positional binary? There's our first two numbers, 0 and 1. If you want to count in 2 bits, simply repeat that pattern. Put zeros in front of the first half, ones in front of the second. Okay, there's how we count with 2-bit numbers. If we want to count with 3-bit numbers, repeat that pattern. Put zeros in front of the first half, ones in front of the second half. There's our regular 3-bit numbering. Okay, that's weighted positional notation. If we want to do this in gray code, it's almost the same procedure. Start off 0, 1. That's our first set of numbers. But to do a second bit, instead of repeating this, reflect it. 0, 1, 1, 0. And put zeros in front of these and ones in front of these. That's our 2-bit gray code sequence. If we want to do 3-bit gray code, take this pattern, repeat it down here, but reflect it. So 1, 0, 1, 1, 0, 1, 0, 0. And now put zeros in front of these and ones in front of those. There's a 3-bit gray code. So that's the reflective part of reflective gray code. So that's a good old 250 flashback. Oh, that's okay. Izad's an awesome teacher for those courses. All right. Let's talk about shortest paths. So this is a pretty classic problem in graph theory. Is you've got a graph, you've got vertices, you've got edges, and you've got some kind of weighting. And your question is, assuming there is at least, a path from one vertex to another, you can find the length of that path, and if there are multiple paths, which path has a shortest length? And so let's make a graph. And let me label these. And let's suppose we want to find a path from A to H. And let me put some weights in here, and I'll put this in pencil because I might want to change these if our weights come out uninteresting. I don't know if this is going to work or not. Well, it'll work somehow. All right, so there's a graph. Totally random edge weights added on here. So we can calculate the cost of going from one vertex to another. All right. For example, to go from C to D, I can do that with a total distance of 2. So think of these as distances, or travel times, or the cost of the toll on the road, or something like that. So if I want to go from C to G, I have a couple of ways to do it. I could go from C to E to G. That's going to be a total distance of 1 plus 7 is 8. I could go from C directly along this edge to G. That's also a distance of 8. I could go from C to D to G. That's a distance of 2 plus 1 is 3. And so our question is, what's the shortest path from one vertex to another? In this case, from A to H. So we want to start here and we want to end up here. And there are lots of paths we could choose from, right? Starting from A, we have 2 possible edges we could follow. Once we get to B, we have 2 edges. Once we get to C, we have 1, 2, 3, 4 edges. This can get combinationally really large. If this was a fully connected graph where every vertex was connected to every other vertex, we would have something like n factorial or n to the nth possibilities to get from one vertex to another. Now this particular setup, we have weights on each edge, and the weights are always positive, and that's important. We're not going to recurse, actually, surprisingly. This is not going to be recursive. There's an iterative algorithm for this, and this is called Dijkstra's algorithm. And a greedy approach is not going to work here. A greedy approach would say, well, starting from A, let's follow the shortest edge. That would be from A to C. And then let's follow the shortest edge from there, and that would be from C to E, so that's a total distance of 2. And then follow the shortest edge from there, and that's going to be 17. So 2 and 17 is 19 to get here, and 1 is the shortest path from here, and that's gets us to D for 20, and then 2 takes us to F with 22, and 1 more, 23, to get from A to H. Right, so we're looking at the shortest total weight, not the smallest number of edges, but we're looking at the shortest weight, the shortest sum. So A to C, C to D, D to F, F to H. Yeah, that's probably going to be a good solution. All right, let me make it harder. Suppose that's a 12. So the solution we're going to find is not necessarily comprised of just taking the shortest hop at each point, right? Because, you know, there can be things further down that have really long distances that you have no choice. Once I get to E, right, I have no choice but to follow this edge or to backtrack, right, which isn't going to help. And if this is really big, you know, maybe I should have taken this edge that started with a 2, or I should have taken this edge that started with a 2, or maybe even this 12 to do better than following this long edge from E to G. So you need some kind of look ahead or something, right? Okay, so Dijkstra's algorithm is a nice iterative algorithm that is guaranteed to get us a shortest path. If there's more than one, it'll give us one of the shortest paths. And I don't remember the exact order of complexity. I'm going to say it's on par with, you know, a polynomial of n. It's a nice order of complexity. So we'll work with this more tomorrow, but let me take you through one of these iterations at least to begin with. So we start off with the notion of tentative distances. So I'm going to say, you know, I don't know how long it takes to reach node H, but I know it's no worse than infinity. So my tentative distance to each of these nodes is infinity. And node A, you know, I'm starting from there, so I can reach that in a distance of 0 from A. All right, so A, B, D, F, H. I believe that is the shortest path, yes. All right, so here's what we do. We visited node A. We're going to put a circle around that because that's the node we're already sitting at. So we've reached A in the shortest distance possible, which was 0, because that's where we started. Okay. So we're going to do the following things. Relax adjacent nodes. Okay, what does that mean? We've circled, this node because this node has been visited. We're going to look at every node that's connected to a node we visited, and we're going to say if we take the distance it took to get here and we add this distance, do we get a better estimate than the current best guess for the distance to this node? In other words, it takes no distance to get to A because we're starting there. If I go 2 more, 0 plus 2 is 2, I can get to B in a distance of 2. 2 is better than infinity. It's smaller than infinity. So we're going to relax that node, which means we're going to replace it with that smaller distance. 0 plus 1 is 1. I can get to node C in a distance of 1. That's better than infinity, so I'm going to relax that distance and say their tentative distance to node C is 1. I'm only going to relax nodes that are adjacent to the node that I just visited, which was A. So I'm not going to continue and relax this and so on. I'm just relaxing those two. And then we're going to visit the closest node. So we're going to say which node in this collection that we haven't already visited, which node is closest. And there's a node with a distance 1, a node with a distance 2, and a bunch of nodes with an infinite distance. So 1 is the closest node, so we're going to visit that next, and we're going to circle that. Once we circle a node, we know that this is the shortest distance to that node. And we're just going to iterate over these two steps. So now we're going to relax everything that's adjacent to C. So C is a distance of 1 from the start. 1 plus 8 is 9. That's better than infinity. 1 plus 1 is 2. Well, that's better than infinity. 1 plus 12 is 13. That's better than infinity. 1 plus 2 is 3. 3 is not better than 2, so I'm not going to change that distance. I'm never going to make this a larger number. Alright, now I look at the distance of every node that I haven't visited yet. There's a node of distance 2, 13, 9, 17. Looks like 2 is the closest node, so I'm going to visit that. And you just keep doing this. And when you circle H, then you found the shortest distance to that node. So we've got a few minutes. Let me just go ahead and run through this quickly, and then we'll go through this again on Friday. So from node 2, 2 plus 3 is 5. That's better than 13, so I can relax that distance. That's the only node that I haven't visited that's adjacent to B. So now, what's the closest node? Well, there's a 5, there's a 2, there's a 9. Maybe I should have visited this before. Anyway, 2 looks like the closest node, so I'm going to visit this. Alright, this is a distance 2 plus 17 is 19. I'm not going to change that, because 19 is worse than 9. And that's the only node that is adjacent to E that I haven't visited. So now I find the closest node to my visited collection. So this is a distance of 5. This is a distance of 9. Looks like this is my closest node. So I'll visit D, and I'll relax again. 5 plus 2 is 7. 5 plus 1 is 6, which is better than 9. And all the other edges are already visited. So now I find the node that's closest to my collection that looks like this, which is G. So at this point I know I can reach G in a distance of 6, and that's the best I can do. So I'm going to relax nodes adjacent to 6 that I haven't visited yet. 6 and 12 is 18. So that looks better. So I know there's a path from A to H with distance 18, but I don't know if that's the shortest path yet. All right, so I visited the closest node. I relaxed all the adjacent nodes. I'm going to go back and visit the closest nodes. I've got a 7 and an 18. Looks like this is the closest. That's a distance of 7. Relax the adjacent nodes. 7 plus 1 is 8 is better. And that's the only adjacent node. So now find the closest node to our collection of visited nodes. Looks like that's an H. It's the only thing left. And there's our final answer. We can reach H in a distance of 8. Now the other detail, and we'll add this on Friday, is in addition to saving these distances, we would like to save the actual path that leads to 8 with that distance, which in this case was 2, 5, 7, 8, as someone said in chat. All right, so that's Dijkstra's algorithm. It's very, very straightforward. It's pretty easy to code. You'll definitely bump into it. If you do game design, if you do network analysis, if you do anything with mapping, right, this is a really common go-to algorithm for finding shortest paths, which is always a nice thing to be able to do. And the order of complexity, right, we have to deal with n nodes, and in each case we might have to deal with, you know, n nodes adjacent to it that we're going to relax, right? So it's something like an n squared algorithm. And it's really not that bad. All right, so we are out of time. We will finish up talking about graph theory on Friday. We'll go through some more examples of Dijkstra's algorithm. I'll probably have you do some of the work, and we'll talk about traveling salesperson, and then we'll move on to our last unit, which will be grammars and languages. All right, cool. Have a good one. I will see you next time.